Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at lesson 8.2.2. This is officially called Exponent Rules. And we're going to actually build on what we did from the first part of lesson 8.2.1, where you were introduced to the basic idea of how exponents work and how you can take exponent expressions and simplify them. But that was just an introduction with the most basic type of exponent operation where you're taking and multiplying two powers together. Today, we're going to take a look at that and expand on it a little bit, and then introduce a couple more properties where you're doing something a little bit different than just multiplying two powers together. So let's go ahead and get to it. It says, in the previous lesson, you expanded expressions written with exponents into factored form and then rewrote them in a simpler form. You also looked at ways to rewrite very large numbers in scientific notation to compare them more easily. In this lesson, you will continue to develop ways to rewrite expressions using exponents. Use the questions below to focus discussion today, or thinking at any rate. What part of expression is being raised to a power? What are the factors, and how can we rewrite the expression to have fewer terms? Okay, so this is what we worked on at the beginning of lesson 8.2.1. This particular property that we're using here is called the product of powers property, right? So it's product because you're multiplying these powers together, and this is a power and this is a power, and technically those are powers too if you think about the fact that the exponents would be ones, right? But we don't see them, we don't use them, they're ninja ones. There's no reason to say to the first power, it's just understood that it's to the first power. So what we want to do is we want to copy these three expressions down, then we want to expand them out, count the number of tens being multiplied repeatedly together, and then count the number of x's and the number of y's, and then put it all back together as a simplified expression. Same thing here, same thing here. Go ahead and pause and see if you can work that out. And then when you are ready for the reveal, unpause, and I will show you how to get to these answers. All right, let's see how you did. So starting with the first problem, we've got 10 squared times x to the third times 10 times y. So if we expand that out, 10 squared is 10 times 10, x to the third is x times x times x, and then you got one 10 here and one y there. So when all of these are put together using commutative property, you can see you've got a total of 3 10s being multiplied together, 3 x's being multiplied together, and then a single y. So we would simplify this expression to basically have the 10 be absorbed into this power to call that 10 to the third, x to the third, y. For problem B, this is where we start appreciating the fact that we can apply a rule to the situation rather than expand it out completely, because you're starting to run out of room here. And if this was 20 to the 30th power times 20 to the 80th, nobody wants to expand it out 110 times. So you got 1, 2, 3 20s being expanded here for the 20 to the third, and then you've got 8 more, 1, 2, 3, 4, 5, 6, 7, 8. And so to rewrite that, we would just count up the total number of times 20s being multiplied together, and that is 11 times. So this ends up being 20 to the 11th power. Here we expand it out, and it's getting even tricky there, where you got x times y times y times z times z times x times x times x times z times z times z times z times z. Now we'll move and cluster all the x's together and all the z's together. There turns out to be a total of 5 x's repeatedly multiplied, 7 z's repeatedly multiplied, and then these 2 y's there didn't have any other y's to move in with them. So we're just going to write that as x to the 5th, y squared, z to the 7th power. So you might already be thinking about a rule that we would apply to this situation, and we'll get to that in a little bit. All right, so here's a stoplight problem, meaning that we have a common mistake that is made with students. Aaron wants to rewrite the expression 5 squared x squared times 5 to the fourth x to the third in simpler form. This is how she expands it out. She writes 5 times 5 plus x times x plus 5 times 5 times 5 times 5 plus x times x times x. So she writes this as an addition problem instead of as a multiplication problem. So what's the problem here? Well, first off, this is all multiplication. There are no plus signs in there. So we do not add any part of this expression together. Well, I shouldn't say we don't add anything, because there is a rule that we need to apply here. But the bases or the powers are not being added together. So if we were to truly write this out the way it's supposed to be written out, where exponents represent repeated multiplication, not repeated addition, we would say x squared is, I'm sorry, 5 squared is 5 times 5. X squared is x times x. 5 to the fourth is 5 times 5 times 5 times 5, and x to the third is x times x times x. And all of those are being added together. So we can take all of the 5s that are being added together, 1, 2, 3, 4, 5, 6 of them, that becomes 5 to the 6th. And then all of the x's, 1, 2, 3, 4, 5, becomes x to the 5th. So this expression simplified becomes 5 to the 6th, x to the 5th. All right, so just like we did at the beginning of lesson 8.2.1, I would like for you to take this and create this table. And then I want you to follow this pattern here of expanding this out into factored form. So here you see 5 squared inside parentheses raised again to the 5th power. That means that this 5 squared has to be repeated 5 times, right? So 5 squared is 5 times 5, and we need 5 of those 5 times 5s. So you got 1, 2, 3, 4, 5 of them. And since all we're doing is multiplying together, we technically don't even need to have those parentheses in there. The parentheses are meant to give priority to an operation that doesn't already have the highest priority. All we're doing is multiplication, so there's no reason to give priority to some of the multiplication and not the other parts. So you can technically remove all the parentheses now and just count up the number of 5s. You got 10 of them repeatedly being multiplied, so we're going to call that 5 to the 10th power. Okay, so let's do this again one more time, and then I'm going to let you do the next 3. 2 squared raised to the 4th power means we're going to expand that 2 out, or the 2 squared, 2 times 2. And now this exponent says you got 4 of those being repeatedly multiplied. So that becomes 2 times 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 2. Well, how many total 2s are being multiplied all the way across? There would be 8 of them. So this simplifies down to 2 to the 8th power. Now, I would like for you to focus on what you see here and how you might derive this 10 as your exponent once it's put into simplest form. Take a look at those 2 numbers there. How would you derive the 8? What do you think is the rule that we use whenever we're using the power of a power property? Okay, go ahead and pause. See if you can figure out the rest of them and see if you can formulate that rule. All righty, let's see how you did. So you've got here 3 to the 7th power, so that is 7 3s being repeatedly multiplied together, and then we're going to take that quantity and we're going to do it again. So here are your 7 3s, and now since it's being squared, that means we're going to take this quantity and multiply it times itself. So how many total 3s are being multiplied together? Well, a total of 14 of them, so that becomes 3 to the 14th power. Here you got x to the 3rd. Here's your x to the 3rd, and then how many times is that going to be repeatedly multiplied? 5 times. So how many total x's are there all the way across? A total of 15 of them. And then this last one gets a little trickier because we're going to have to eventually use some commutative property. But the basics are to expand out x times x times x times y, and then we're going to do that again, right? This quantity squared means this quantity times itself. So now how many total x's are there? You got 1, 2, 3, 4, 5, 6 x's being multiplied together. And then how many y's are being multiplied together? You got y times y and y times y for a total of 4 of them. So that becomes y to the 4th. So in simplest form, this expression becomes x to the 6th, y to the 4th. Okay, so what do we call this? We call this the power of a power property because we're starting with a power, and then that in itself is being raised again to a power. Unlike the previous property, which was the product of powers, where you're taking two powers and you're multiplying them together. There's a different rule that we apply here with the exponents compared to what we do here with the exponents. So it says, work with your team to describe the pattern between the exponents in the original form and the exponents in this exponent form. And hopefully you recognize that here, let's just look at this problem here. You had a 3 and a 5 were your exponent, and in simplest form it becomes 15. So what are we going to do with those exponents? We are going to multiply exponents together whenever you are taking the power of a power. So visualize 20 to the 3rd raised again to the 8th power written in factored form. What is being multiplied? That is what is the base in this situation. And then how many times is it being multiplied together? Okay, can you go ahead and address this question and see if you can formulate your thoughts and write down your ideas about what is being multiplied and how you would rewrite this in simplest form. Pause and work through that, and then I will reveal in a second. All right, let us see how you did. What's the question again? It's saying, visualize this written in factored form. What is being multiplied? Okay, so it's the 20 is the base, right? That's what's being repeatedly multiplied. Now it's being repeatedly multiplied 3 times for 20 to the 3rd power, and then that is being repeatedly multiplied 8 times. So in essence, the base 20 is being repeatedly multiplied here when all is said and done 24 times. How does that work? Well, whenever you're taking the power of a power, you just multiply the exponents together and you keep your base. So if you could picture this completely expanded out, let me go ahead and do this using very small writing, 20 times 20 times 20. Okay, that's 20 to the 3rd power. Now we're going to do this 8 times. Right, that is 1, 2, 3, 4 times. And I'm going to use my little cheat button to do it another 4 times. And then you can physically count them up. 3, 6, 9, 12, 15, 18, 21, 24, total 20 is being multiplied together there. All right, so in problem 59, you simplified the expression 20 to the 3rd times 20 to the 8th. Compare the factored form you wrote for that expression to the expression you visualized in problem number 61, and how are they different? Okay, so the first one was a product of powers kind of a property. And so you would just take 20 to the 3rd, 1, 2, 3 of them, and then 20 to the 8th, 1, 2, 3, 4, 5, 6, 7, 8. And how many total times is the 20 being multiplied together? 11 times. So the shortcut would be to take, when you're multiplying powers together, you add them and keep your base, right? Product of powers. Keep your base, add your exponents. Now when it's the power of a power property, did I have room to do this? Oh, there it is right there. 20 to the 3rd raised again to the 8th power. The shortcut is that we will just stop it. The shortcut is that we would just multiply those powers together. Okay, so this is a rule that you have to remember. It's not easy to remember because there's quite a few rules. You're going to find in our M&Ms that you're going to write in after the homework on Thursday is for all the exponent rules. There's a lot of different details to remember here. So that's where it's so important to visualize how it would look if you were to expand them out. And by visualizing it expanding out, it helps inform what the rule is for each situation. Okay, so the idea that you expand this to 23 times and then 28 times for a total of 11 20s being multiplied. Okay, so you know you add the 3 and the 8 together. That's the rule for product of powers. And the fact that this is being repeatedly multiplied 8 times means you're going to have a lot more. 3 times 8 is 24. All right, so Heidi's trying to rewrite the two expressions below. This says 2x to the third power, and this says 2x to the third power. Notice when I say both of them, they sound exactly the same. But having parentheses in one of them changes the dynamics of the expression. If it didn't, then there'd be no point of having the parentheses there. So remember, exponents have the higher priority when you are doing the order of operations. This has two different operations taking place here. You've got multiplication, 2 times the x, and then x to the third power. So you would have to do the exponent first before multiplying. But in this case, parentheses are around the 2 times x, which means you have to do that first before you raise to a power. So that's going to change the answer. Okay, so go ahead and take a look at these 3 questions, A, B, and C, and I want you to respond to each one of them. First says, A says, rewrite 2x to the third by expanding and then simplifying. What part is being raised to the third power? For B, Heidi thinks 2x to the third is the same as 2 times x to the third. Show that she is correct by expanding it out. And then the third, are they equivalent? Explain why or why not. Okay, take your time with that. Formulate your answers and then unpause when you're ready for the reveal. All right, let's see how you did. So if we rewrite this, it is literally 2x times 2x times 2x, right? This quantity raised to the third power. Now, if you were to rearrange that using commutative property, get rid of the parentheses and just show it as all multiplication, you can put all the 2's together for 2 to the third and put all the x's together for x to the third. So once you fully simplify it, this becomes 8x to the third power. Or if you just left it in exponent form, 2 to the third times x to the third. This, the exponent only applies to the x, not to the 2. So when we expand this out, 2x to the third power without the parentheses becomes 2 times x times x times x, which, stop it. Why you do that? That's crazy. Which becomes 2x to the third, just as she was stating. So this is already in simplest form, whereas this one was not. So are they equivalent to each other? No, they are not. And this is the basic rule that I would like for all of you to follow. Apply this rule. The exponent, let me say that again. The exponent only applies to what it touches. So in this case, the exponent is touching the parentheses, so it applies to everything on the inside of the parentheses. This one is only touching the x, so it does not apply to the 2. So this introduces a new property, which I'm not going to have you write it down yet. This is called power of a product property, where you're taking something that's being multiplied together and you're raising it to a power. And basically what this says is you're going to use distributive property here. You're going to apply it to the 2 as well as applying it to the x. But it isn't distributive property. I want to make that clear. I'm just saying it's like distributive property, where this exponent goes to every single factor that's inside the parentheses. So it applies to the 2 and it applies to the 3. And since 2 to the third is a relatively easy number that we can evaluate, I chose to write it as 8. But since we don't know what x is, we'll just leave that as x to the third power. All right, this is the last property that we're going to address today. It's called the quotient powers property. And you may recall from back in 3rd and 4th grade, the answer to a division problem is called a quotient. Since fractions technically are division problems, this represents a quotient. Okay, so once you simplify it, we'll have the quotient of this division problem that involves powers. So AJ was trying to simplify the exponent expression 5 to the 7th divided by 5 to the 3rd. He started by writing out in factored form. Once he saw it in factored form, he recognized a giant 1 in his work. So copy this expression on your paper and then expand it out. So how does that look expanded out? I'm not gonna, I'll just let you copy me down. You got 5 to the 7th power in the numerator, so 5 times 5 times 5 times 5 times 5 times 5 times 5, 7 of them, and 3 of them on the bottom. Oops, I don't want that little dot there. Get out of there. Okay. So you see the giant ones in there? I hope so, because that would be a giant one. This would be a giant one, and this would be a giant one. So in essence, this becomes 5 times 5 times 5 times 5 times your giant one times your giant one times your giant one. And we all know whenever you multiply something times 1, it doesn't change its value. So we're not going to worry about that. We're just going to leave it as 5 times 5 times 5 times 5 because these guys essentially cancel each other out, leaving you with what's in the numerator. And how would you write that expression in simplest form? Well, you would write it as 5 to the 4th. So here's the rule. When we were multiplying powers together, you added the exponents. So now when we are dividing powers that have the same base, you are going to keep your base and you're going to subtract the exponents. And you see the subtraction is because of the giant ones that are being cleared out of there. Okay, so the more times you expand this, the more it'll make sense that you just do a subtraction. 5 3 times in the bottom cancels out 5 3 times multiplied in the numerator, leaving you with 4 in the numerator. And technically, I guess this really looks like that, which becomes 5 to the 4th over 1, which is the same as 5 to the 4th because you don't need a 1 in your denominator. So we now have 3 properties for exponents that we've been introduced to, and now let's go ahead and practice. Copy down these 4 expressions, expand them out, cancel out the giant ones, and then rewrite it as a simplified expression. Alrighty, let's see how you did. This will end our lesson today. So 2 to the 4th over 2 to the 2nd can be written as this, and you may have noticed that you got a giant one here and a giant one here. So if you take 2 to the 4 minus 2, 4 minus 2 is equal to 2, so that is wrong, 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 wrong. Hold on for a second. Yes, that is correct. 2 to the 2nd power is our answer. Here, oh my goodness gracious, hold on for a second. Okay, we got it. Everything clarified. All right, so here you got 3 to the 4th in the numerator and 3 to the 5th in the denominator. So if you were to find your giant ones and cancel those giant ones out, you'll notice that everything from the numerator cancels out, but you still got a 3 in the denominator. Now, this is where you need to think about what we did when we were working with simplifying fractions in the past. Remember, if everything in the denominator cancels out, there's no real reason to put a 1 in the denominator. You just leave it, whatever's in the numerator is the answer. But when you cancel out everything from the numerator, you still have to have that 1 there. So this is how this becomes 1/3, okay? For y to the 7th, that's in the numerator, divided by y to the 4th, you're gonna have 1, 2, 3, and maybe I'll do 4, I'll do that one, leaving you with y to the 3rd power with nothing in the denominator, so that ends up being your final. And then for this one, we're going to expand out x to the 3rd, y to the 2nd, and then in the bottom, x times y to the 2nd. So what do we have here? You've got these x's cancel out, forming a giant 1, and the 2 y's on the top and bottom cancel out, leaving you with x squared as your simplified expression. Alrighty, so there you go. We've got 3 new rules for us to learn. We've learned it, now it's time to practice it, and eventually we are going to master these rules. All right, let's move on to our check for understanding. Take care, bye.
Hey, feeling good, like I should. When in dark,